So in this recorded module, we're introducing the divergence theorem, which is the last and maybe biggest, maybe most useful, maybe result in vector calculus. If you look at where we've come from to get here, prior to this, we were talking about Stokes' theorem. And we had Stokes' theorem itself encapsulated a whole bunch of things we've talked about in this course. The Stokes' theorem said that if you looked at, you had a vector field F, and if you looked at the contour integral of F around any closed contour, around a closed contour, it would be equal to the flux integral of the curl of F through any surface bounded by that contour. So if the contour was a wire and the surface was a soap bubble that was bounded by that closed loop, if you look at F dot dr around that loop, it would be equal to the total flux of the curl of F through any surface bounded by the loop. And it didn't matter what surface it was. So it was kind of a surprising, a very general result. Sometimes powerful, sometimes less so. Back in one more step, in the special case where that contour was in the plane, then the Stokes' theorem just became Green's theorem. So Green's theorem was sort of an introductory special case to Stokes' theorem. So now what we're going to find or look at is sort of a next level geometric theorem. So we're going to find or show that the divergence theorem says that if now we look at a closed surface, okay, and a volume bounded by that closed surface, okay, if we take the total flux of F through that surface, not the flux of the curl of F, the flux of F, okay, the flux of F through a closed surface will equal the triple integral of the divergence of that same vector field over the region enclosed by that surface. Now, when we talk about divergence, there's not like any volume, any surface. There's, you have a closed surface that defines a unique volume. It doesn't have that same feature that Stokes did. Okay, but so we're relating a double surface integral to a volume integral or triple integral. The symbology, right? We use a double for a closed surface. Like when we do a closed contour, we draw a circle in the middle of the integral. For a closed surface, we do a double integral with a loop there. That indicates closed surface. In the typeset notes, I don't generally use that because it's just a difficult symbol in LaTeX to produce. But it's clear from the problem when we have a closed surface and when we don't. So this is the statement, right? This here is a statement of the divergence theorem. Okay? And it's called the divergence theorem because the divergence of F is what we're integrating in the triple integral. Technically, right, D has to be closed and bounded. Yeah, has to be closed surface. The surface bounding this does not have to be smooth. It can be piecewise. It could be like a cylinder. You have a flat top, then sides, and a bottom. You have to close it. You have to have all the surfaces there, but it can be piecewise smooth. Okay. The boundary S, remember when we talked about flux, you had to decide what direction through S was positive. So when we do this theorem, it's the outward normal that is positive. Okay? And you'll see that in the first problems we do, as opposed to the inward normal. So outward normal, that's positive, that gives us this. Right? The vector field F with its various components, they have to be well behaved. They have to be continuous and have continuous first derivatives on D, which really just allows us to calculate the divergence itself. Okay. So what I'm going to do in the note module, that's called the divergence theorem for 2276. I do this problem on the right-hand side, but I do it longer. I do it both ways. I do the surface integration and the triple integration of the divergence. Here I'm just going to quickly do the divergence theorem part, and I'll record another module where I do the whole problem again, but longer. Just because this, when we're introducing divergence theorem today, this is long enough. So let's look at this simple example. Let D be this region, three-dimensional region, bounded by the hemisphere x squared plus y squared plus z minus 1 squared equals 9, where z is limited between 1 and 4. Okay, and the plane z equals 1. Okay, so those two, this surface, which is a hemisphere, and this surface, which is a plane, those two describe the region. Okay, so it's actually shown here, and it's a little bit redundant. This 1 z between 1 and 4 is actually redundant. If we just said, here's a sphere, I want the upper half above the plane z equal 1, that's all we would have to say. Because this is the equation of a sphere centered at 0, 0, 1. Okay? So I've drawn it here. It's like it's an upside down bowl. It's a circular bowl. It's half of a circle, of a sphere, raised up by 1 unit along the z-axis. That's all. And then we have a flat bottom. Okay? The plane z equal 1. So that's the surface, or that's the region, and also defines the surfaces. Okay? So easy enough. Okay? Separately from this, and it's a little deceptive because it almost looks similar, but they are unrelated. Separate from the surfaces and then thereby the definition of the volume, we have the vector field. So the vector field happens to be xi plus yj plus z minus 1k. Okay. And we're asked, calculate the total flux through S bounding D. So when we think about this surface, the surfaces that are the upper upside down bowl and the flat, I want the total flux through those surfaces. So I could do that using methods we talked about in the past weeks. I could just do 2 surface integrals. They're actually not that hard, right? And I would just be calculating this directly by itself. Okay? But what we're going to do now is we're just going to instead use the divergence theorem result. And for these first problems, they're set up to be totally trivial. They just fall down in the face of divergence theorem. We'll quickly do more problems that aren't quite so trivial. But so, this is the problem, right? It's stated as a flux calculation, and we're going to use the divergence theorem result to calculate that flux. So, I'll just leave this guy up here for a sec. If we're doing this, right? The first thing we would do is, okay, well, we got f. Let's get the integral. Let's get the integrand. Let's calculate the divergence of f. So I need the divergence of f. Right? So that is di by x of the x component. So that is di x of x plus di by y of the y component of f, which happens to be y. You can see this is set up to give a simple result. Plus di by z of the z component, z minus 1. Right? So this equals 3. 1 plus 1 plus 1. Okay. So, the total flux then, right, which is this value, would be equal to the triple integral of d of the divergence of f dv, which happens to be the triple integral over this region of the number 3 times dv. So this just becomes 3 times this. Now, so this problem again is contrived to be very simple because as soon as the divergence is a constant, this thing just turns into the volume. So it says it's 3 times the volume of that region. What's the volume of that region? Well, it's 1/2 the volume of a sphere radius 3, right? So this thing would be 3, let's add 3, right down here, 3 times 1/2 the volume, 4/3 pi r cubed. R is 3 here. So 3 to the 3rd, right? So this just becomes 3 cancels 3. This becomes 2 pi times 3 times 3 times 27. So this is 54 pi. That's the final answer. So, and it would have units of flux, so whatever units F has times meter squared, right? So, okay, super. And you compare, right? This would be, if we were doing it the flux way, I'd have 2 flux integrals. I'd have to find the surface, I'd have to find the outward normal, I'd have to do a surface integral in the upper half, and then I'd have to do it again on the lower surface, right? And I'd sum those 2 things up, and what I would find is that I would get 54 pi. Generally, the divergence calculation is much easier than the surface flux. The surface flux, it's got lots of pieces to it. We always got to convert the surface down to areas and to equivalent regions, and there's square roots and partial derivatives and all kinds of stuff. So the flux integrals are generally not easy. The divergence results in a scalar field, and usually they're simpler because it's a derivative action, so usually it compresses the function down a bit. But this is this result. This particular example is obviously set up to be very easy. Generally, this integral isn't this trivial, and we still have a triple integral to do. But that's the divergence theorem. Sometimes the divergence theorem is called Gauss's theorem. And remember how Gauss's theorem was used. It's been a while. It was last year in the second half of first year physics. Gauss's theorem, we would use it in electrostatics, and basically the concept was, if you look at the total flux of the electric field through a closed surface, the total flux was equal to the total charge enclosed, okay? Now, it didn't mean that the flux was zero on the surface. It meant that the sum of the flux was zero on the surface. And so in cases where you could have certain symmetries and you could sort of guess by geometry what the direction of the electric field was, and if you could just simply assess, well, okay, the total charge inside the surface is zero, then you could deduce the value of the electric field on some of the surfaces. And so Gauss's law became this trick to calculate electric fields in situations of relatively high symmetry. Because in general, the calculation of electric fields is pretty hard, right? It's sort of a Coulomb's law calculation. There are other ways to do it, but it's not easy. But in certain cases, Gauss's law would allow us to do it. And really, the vector calculus underpinning of Gauss's law is the divergence theorem. Okay? It is rare to see this theorem called Gauss's theorem. I almost never see it, but it could happen. But it is, Gauss's law is a result of the application of this theorem. Okay? So now, in the next modules, what we're going to do to finish off vector calculus is we're going to look at some different applications or examples, I guess, of the divergence theorem. And we're going to look at more or less difficult ones. We're going to look at a problem where we verify it, where you calculate both sides of the problem and show they're equal. We're also going to extend this to cylindrical and then spherical coordinates, and in particular look at divergence theorem in that context. And that'll finish off vector calculus.